Welcome back to Math 104. Each computer from a certain manufacturer has a 0.95 probability of working properly, independently of the other computers in the same shipment. That means that each computer is its own Bernoulli trial, with a probability p equal to 0.95 that it does work. Every computer either works or doesn't work, and this is the probability that it does work. We're also given this additional information that each properly working computer will result in a $100 profit for the manufacturer, but each defective one will result in a $50 loss. That is separate information from what the Bernoulli trial is in and of itself. Our question is, how many computers do you expect to work properly in a shipment of 200 computers? This is the most basic expected value question we can ask in this context. Namely, what is the expected number of successes in 200 Bernoulli trials? This can be formulated as how many successes? What is the expected number of successes in a certain number of Bernoulli trials? Because it can be formulated in that basic way in terms of number of successes in so many Bernoulli trials, it is a job for the NP shortcut. Here the number of trials equals 200, and the probability of success on each trial equals 0.95, so that means that on average we expect 190 computers to work properly. As it turns out, because of the question that was asked, we never used this additional information about dollars, about profits and losses. If the question had instead been what is the expected number of dollars gained or lost, that would have been a different kind of a question, and it would not have been a job for the n times p shortcut. Here is another kind of expected value problem that involves the binomial probability model. This is an important practical example having to do with efficient blood testing. The contrast between individual samples and pooled samples. We'll see what that means. The background is that 20 patients need to have their blood tested for a certain disease. We will assume that each patient, independently of the other patients, has a 1% chance of having the disease, and the test is perfectly accurate. If it's bothering you that we are making these big assumptions, good! That should bother you on some level. These are very big assumptions. That each patient's status of having the disease or not having the disease is independent of everyone else in the room, that's a big assumption. And to say that the test is perfectly accurate, well, that's a big assumption also. Anytime that mathematics is applied, we make simplifying assumptions, and someone at some point has to think about whether or not they're justified. For our purposes right now, we are going to go ahead with this simplifying assumption, but we will come back to this issue of whether medical tests are perfectly accurate and how to deal with it if they're not perfectly accurate. We consider two methods of testing these 20 patients. One is the individual method. You test each patient individually. You probably thought that was the only thing you could do. You draw blood from each patient and apply a test to each individual patient's blood sample. This guarantees that exactly 20 tests will be performed. And you're thinking, well, what else could you possibly do? This is the other thing you could possibly do. And that's the pooled method. You could draw blood from each patient and then combine the blood drawn from all 20 patients into one sample, and then test that one pooled sample of blood. Let's think about this. If the pooled sample of blood tests negative, that means that there's no evidence of the disease anywhere in this sample that contains blood from all 20 people. It will follow that all 20 people are okay. All 20 patients are healthy in the sense of not having that particular disease. However, if the pooled sample tests positive, then someone, we don't know who, someone among those 20 people has the disease. As long as one person has the disease, the pooled sample will register in the test as positive. It might be that 2 people have the disease. It might be that all 20 have the disease. We just don't know. But what we do know after the pooled sample tests positive is that we're going to have to do more testing to find out who actually has the disease and who doesn't, and so in that case we proceed to test all 20 patients individually. Here is our question. Which method requires fewer tests on average? Now that's an important question, because very often medical tests are quite expensive. A hospital which has more efficient ways of carrying out its medical tests, and still doing it effectively, will be able to do a better job of using the resources that it has. Resources are always finite, and so there will always be genuine practical questions like this one. The key point for us right now is to understand that this is really asking for an expected value. The key point for us right now is that this is really asking for an expected value. We are really asking which of the two methods has the lower expected value, the lower expected number of tests. For the individual method, we don't need to do any computing. The expected number of tests, the average number of tests, is exactly 20, because every time you use the pooled method on 20 people, you will have to perform 20 tests. So for the individual method, the average number of tests to be performed equals 20. For the pooled method, we need to do more of a computation. For the pooled method, we need to think, what are the different possible numbers of tests we might need to perform? If the pooled sample tests negative, then we are all finished after one test, we send all the patients home, fantastic. There's no more that needs to be done. However, in the other case, that the pooled sample tests positive, then we have to do these follow-up tests, and in that case, it's not 20 tests, but 21 tests overall that need to be performed, because you have that initial test on the pooled sample followed by the 20 individualized tests. So when you apply the pooled method to 20 patients, either you have to apply one test, or you have to apply 21 tests. To find the average number of tests under the pooled method, that means taking a weighted average of 1 and 21, where they are weighted by their probabilities. So we have to compute one test times the probability of one test. And we'll think in a minute what that is, but we're adding to that 21 tests weighted by its probability. So 21 tests times the probability that we will need to do 21 tests. So this equals one test times the probability that everyone is healthy. That's what would have to happen for us to get away with doing only one test, and that is a job for the binomial probability model. Right? Each individual patient is a Bernoulli trial. Each individual patient is either healthy or not healthy, at least as far as this one disease goes. We said that each person has a 0.01 chance of having the disease, and therefore a 0.99 probability of not having the disease. So we're computing 20 choose 20, so the probability that there are 20 people who are healthy, times 0.99 raised to the 20, times 0.01 raised to the 0. This is mathematically equivalent to an experiment where we flip 20 coins, and each individual coin has a 99% chance of showing heads and only a 1% chance of showing tails. If you wanted to compute the probability that they all show heads, that's analogous to all 20 patients being healthy, this is the probability you would have to compute. So we add to that 21 tests times the probability that we do need to apply 21 tests. If at least one person has the disease, that's what makes us have to do 21 tests. So the probability that we're in this scenario of having to do 21 tests is exactly the complementary probability, 1 minus the probability of having to do only one test. This is approximately equal to 1 test times 0.8109 plus 21 tests times the complementary probability, which is 0.1891. Here we see our weighted average. We might have to do one test, we might have to do 21 tests, but the good news is there's actually quite a high probability that we only need to do one test. And so when the number 1 is weighted by its probability, that drags the overall weighted average down quite a bit. 21 is being multiplied by a small probability, so it's not pulling the weighted average up very much. We compute, and this turns out to equal approximately 4.64 tests. That makes the pooled method much more efficient than the individual method, which required 20 tests. That difference between an average of 4.64 tests for every 20 patients and 20 tests for every 20 patients adds up to serious money if each test is expensive. Over the course of a year at a hospital, that can be a huge difference. This kind of an expected value computation really is practically important. Please go on to the next video where we'll discuss another kind of expected value problem.